So let's see if we finish off. You know, we're already midway through the virus thing, and then the fungi is pretty. The class of the fungi looks like a botany class we talked about, but it's pretty easy. So on the viral side, so we mentioned last class that we went, you know, from the bacterial side, certain characteristics of bacteria, the way we classify them, shape, form, staining. The other thing that we said that is like, we are relatively ancient in the way we identify and we get some of those. I think today the genomic side is really the thing that has set us apart, you know, in that place. So at the end on the bacterial side, oh my God, in the bacterial side. Okay, let's give it a time. You know, so she saw something that is just like a Halloween thing or something. You know? So, oh yeah. and then on the viral side, on the virus side of it, what I talked is that shape and size and staining, that's no longer important. Like, there's no way for you to do that. The identification, if you want to be very specific, has to go through, you know, basically their DNA. So you have to go and do PCR or something close to it to identify it. And we were talking about the format. So virus is really this simple thing. The proteic capsule with your DNA or RNA inside. If it is DNA, it is a really what we call a DNA virus. If it is a RNA, we call it retrovirus. And it doesn't really matter. It doesn't mean that one is more infectious than the other and so on. They will have these slightly different ways of replicating inside of the cell, but it's very, I would say, intuitive. Okay, if you are DNA, if you are RNA, basically you're going to have to replicate a little bit in the cytoplasm, produce a few other things, or produce from the RNA your DNA, go to the nucleus, and then do your job. So another thing is, all of your viruses, they will have more or less this sort of structure, not in this shape. They tend to have very geometrical shapes. If you look at them into like electron microscope and stuff, they really look like little transformers. You know, they look weird. But one thing that they have is this capsomere made of, or this capsid, and sometimes they have this external, this envelope. Whatever type or whatever format this is, they will have to have something to anchor into the cell, or basically to attach. One example that I gave was those spikes. Okay? So you might have some of those spikes, and through these spikes, they may attach to the cell, and most often, once they attach to the cell, they go inside the cell by phagocytosis. Same way that, you know, a cell transports, for the most part, liquids in general to the inside the cell. That's the way they do it. If you don't have this envelope, sometimes you have some molecules here in the wall of the capsid, sometimes into the edges of the capsid, that makes them attach to the cell. Okay. Bacteria are a little different, but they have their own way of doing the same. Okay. You're going to see that for fungi, it is a little different, because I know we're moving ahead, but the fungi is more of a, I think for us, I think it's fair to say it's more of an opportunistic kind of agent. It's very, very rare for you to have something from a fungi, and for 95% of the cases is going to be superficial dermatophytosis that we call, which is like, you know, basically, you know, infections of the skin or the upper respiratory tract, or things that are very urinary tract infections, which is very common as well. But those, it will be most of the time, constrained to those systems. If you start having fungi infections, systemic, you're dying. you know, you're gone, you know, midway through, you know, so that's the way. So let's go back to the virus here. We mentioned this, nucleic acid content, enzymes, intracellular activity, and obviously cell death as consequence for the cell. The stuff is like the nucleic acid content, either RNA or DNA or RNA, that will give rise to some messenger RNA that will encode for a certain protein. Normally, the proteins it encodes is for the capsid. Okay, and sometimes one another enzyme. It's very few things. It's a very simple thing. What is the danger then for the that comes from the virus? Is that it replicates like crazy. You can have thousands of viral, or what we call virions, which is the unit, inside of a cell. Once that happens, you mess with the cell, because you concentrate all that activity from the cell that otherwise would have to produce other proteins, other things, only to produce those virions. You end up killing the cell, okay? As I said, attachments, most of the time, you know, you have receptor sites in the plasma membrane of cells. In this case here, distributed over the surface of the virus. Enters by pinocytosis. Sometimes you can enter by what we call fusion, but it's not very, very common. So the next one, obviously you have all these things, the biosynthesis of DNA or RNA viruses. The next 2 slides will probably cover most of that. But basically what happens is something like this. Once the virus it gets inside of the cell, you have a moment what we call eclipse period, which is basically the virus is basically non-detectable at that point. And the only reason that happens is that at some point when the virus gets inside, you have the capsid with the nucleic acid inside, but that capsid will have to disappear at some point. Why? Because you want that DNA, let's say a DNA virus, to go inside the nucleus. Okay, so basically you destroy what was the unit of the virus. And then you separate the viral nucleic acid from the coating, and then or from the capsid, and then it becomes this non-enveloped capsid. And then after that, that nucleic acid goes inside. If it is a retrovirus or RNA virus, it will replicate and will form a DNA molecule actually in the cytoplasm. Okay? You use some of the machinery in the cytoplasm, form the DNA molecule. That DNA molecule then goes inside the nucleus, and in the nucleus attaches to the chromatin, and from the chromatin then starts to produce proteins or mRNAs that will give rise to probably the capsid and other things that the virus might need. Eventually, once you produce all of that, the virus have ways to put them back together. You're going to produce more of the DNA, or the replicating the DNA of the virus, or more the RNA. That thing all goes to the cytoplasm. It gets together with the proteins that were produced. Then you form the new capsid or the new virion unit. And then eventually, either the cell, if it dies, it can burst and then, expel all these virions that will then infect more cells. Or what may happen is that it starts forming little vesicles that then transports this to the outside. And sometimes when we say like the envelope of some of these viruses are the actual remnants of the plasma membrane of the cell that they just killed, which is very smart. Why? Because you can hide a little bit. Okay, so you're not running, so you have a little bit of a protection, and at the same time is a protection from a cell that is self, that is from the host. Okay, that provides a little bit of something there. Okay, so this is biosynthesis of the DNA virus. Again, enters, attaches, goes into like it can goes like in the pinocytosis. Sometimes this vesicle breaks down, and then you have the actual DNA with the capsid proteins going somewhere. This DNA goes inside of the nucleus, attaches to the chromatin, starts to produce mRNA. This mRNA starts to produce, then goes outside, starts to produce proteins that is probably more capsid proteins. Eventually, you have the whole thing, the whole shebang, with lots of DNA from viruses, with lots of capsids, and they get together, and eventually they get expelled. The only difference then for the RNA virus is that the RNA, you're going to have your viral RNA first doing reverse transcriptase to a DNA, and then this DNA will go then inside and do the same thing. Okay, so it's just a little switch there when you call this reverse transcriptase. This is not something that lots of the eukaryotic cells do. Okay, you don't go from RNA to DNA, but if you look at how they are produced and all that coding, unless as long as you have the enzyme to do that, it shouldn't be a problem. You should be able to produce a DNA molecule from your RNA molecule. And that's it. On the case, if you make the same comparison to the bacteria side, the bacteria, so if you want to do this, I think we mentioned before as far as the, how do you know, and some of the tests that you do, you incubate in actual cell lines, or you incubate even in another animal to see, how it works. If you compare this to the bacteria side, and the bacterial side, you almost never do that, because you can replicate in other ways, in ways other than just infecting a cell line. Okay, so you see that aside from the fact that the virus will at some point will burst and will leave the cell, the majority of time the virus is inside the cell, killing cells, which is a little bit different than bacteria. Bacteria, most of the time, they are outside the cell, okay? Which has major implications in terms of treatments for these conditions. Take, for example, I think I mentioned before that superbug, Staphylococcus aureus, that you see lots in dairy, which is the field that I work with. Once a cow has an infection in the mammary gland with Staph aureus, is a nightmare, because you cannot get rid of that bacteria. And one of the reasons why they cannot get rid of the bacteria is, guess what? Staph aureus can be, or are, or is an intracellular bacteria. Somehow it gets inside and stays there, which basically means for antibiotic to get access to the bacteria is a pain. For you, even your own anti or immune system to identify and fight is a problem. They have ways to hide. So every time you get something that is intracellular, it normally becomes a problem, okay? Because your cell was made in a certain way to kind of hide inside yourself. So it's a very tricky way. Cancer becomes then a problem too, especially early on, for you to identify. Let's say right now is very possible that all of us here have mitosis happening somewhere that is not 100% right. Why not all of us will eventually get cancer? Because your immune system is good, healthy, will somehow identify those cells. Dendritic cells, macrophages, they're fighting for you. That's how and they're killing those cells. Why? But they have is an internal way of identifying those cells, which is different. There's no way for you to all of a sudden, okay, let's, take something, a medication or something, and we're going to prevent all cancer cells from coming. Unlikely for you to do that. Very good. Other thing that happens, and this is something that is different from bacteria, is this concept of latency in viral infections. Viruses, because they can hide inside of the cell, they also have somewhat strategies to, not all of them, but some of them, they have strategies to become quiet at certain moments, either in their life cycle or dependent on the immune system of the host. If they perceive that the immune system of the host is weak, they come back. But if they perceive you're healthy, they just hide. Just stay there. And imagine, they can be inside the nucleus of cells and basically replicating as mitosis goes. Because during mitosis, you also, so they can incorporate into the, it's unbelievable. You know, if you think about it, it's a very, very nice strategy. So they get into what we call equilibrium with the host, no disease. It's different than persistent viral infection, which is what we call a chronic infection. So one of the examples can be HIV. The other example could be this bovine leukosis virus. And basically what it is that in these two cases of the persistent chronic infection, the animal has a disease. It's different than the latent one, which the animal is basically healthy. The other one, you do have a little bit, you still have problems, you still have something going on there that doesn't, you know, if you don't have any drugs or don't treat a human with the HIV virus from replicating, you will have your immune system depleted. This is a condition. It's not like they disappear. Okay, so and then you're gonna die of flu. You're gonna die of whatever. So lots of this stuff that I normally say that, you know, we in immunology, in biology, lots have been learned in the immune system because of HIV/AIDS. Why? Because we had to study immunology to a certain extent that, you know, if you look at immunology books in the 1980s, 1990s, they look nothing like what they are now. We are so much more advanced on how we understand the immune system, which is like a freaking complicated system. But we know, for example, that without, imagine, and this is like super sad, and in a way we found out. So once you have those T cells depleted because of HIV, people start dying of anything. Flu, because you don't have more immune system. People start dying of cancer. That happens all the time. Why? Because you don't have any more a system that checks your body around. So lots of deaths in the beginning from HIV actually came from the end result was cancer. It was not even, or you have people that used to have, when I said like in the case of fungi, lots of yeast infections, for example. Why? Because you no longer yeast infection, especially systemic. If you start having that, that's is because your immune system is gone, basically gone. So lots of nice little development, but at the same time, extremely, those two cases here, HIV or bovine leukosis virus, no cure. Up to this day, what we do, one, you suppress, the other one, you select, you discard. You cannot select and discard humans, but you do that in bovine. So you start going, it's not like you can send to slaughter, you can send to whatever. But the idea that you found a cure for some, especially this latent viral infections and persistent viral infections, it's something that there's no antibiotic, there's no anti-inflammatory, there's no even antiviral drugs that at this point have been able to basically cure those. You are able to control those, but not cure those. So the next is just a little bit, so this is the most common thing when it comes to virus, which is very similar to bacterial infections. So if you have to have a response, so this is the number of variants. So if you have in terms of, if that was the number of bacteria, that would be very similar to a bacterial infection. But we have these two different ways here in which bacteria is less likely to occur. One is to have one that can really hide inside of you and then eventually comes. And the other one is to have this persistent infection. The persistent infection you can have with bacterial infection. Don't get me wrong. But it's not, I think sometimes they come more like with the state or the condition of the host. In the case of some of this persistent infection in virus, you can have completely healthy or completely, healthy animals, and not completely healthy, but eventually they can come into a certain healthy state that is okay, but they still suffer. They're still okay. They're still not okay. They're still going to having some depletion in some system. Very good. So that's the viral one, and I think by the time we go into the pharmacological principle, and I think this is the part that is mostly the most frustrating, is that we do not have, for animal, we do not have a very efficient, drug or therapeutics against viruses. In humans, as I mentioned before, you can have some in cases of HIV, but it's also like very limited to this disease basically. Today, even the stuff like what is for example, the efficacy of those drugs, antiretrovirus drugs or antivirus drugs, they are actually pretty good. Today they got to a point where they really almost zero the replication of those, but you don't get rid of those. Okay? So antibiotics, anti-inflammatories, eventually during the case studies we're going to go into other types of drugs, but nothing that has to do with virus. Normally virus, for the most part, they still like a problem. Again, fungi, bacteria and fungi are two of those that they can be beneficial or can be pathogenic. It depends on the balance of those. So you're going to have, and we live basically with yeast stuff, the same way we live with probiotics for even to take as nutrition and so on. And they can have like a 500 beneficial things. The only thing, and this portion here, I have one slide of this and the life cycle. I'll be very honest with you. Like, we're going to go through those. I'm not going to ask you anything about the life cycle of the freaking defect. No, it's not going to happen. The only thing is, it tends to be opportunistic. It tends to be really superficial. I don't think it's going to change much from what I already said. And if there is systemic effects or systemic diseases caused by fungi, it is because it is a problem with the host, not necessarily with the fungi. Okay? Every now and then, and I think it was not very long ago that we had a super fungi going on in some hospitals and stuff. And the same way, drugs for fungi is very, actually there is one or two that is normally used for fungi infections. If you look at over-the-counter stuff for humans, lots of the stuff that happens like mycosis or infections of the nail, like athlete's food, and all of the stuff, this is like, it's because the conditions that we put either our feet or the skin, or type of work we do, especially gardeners and farmers that have a lot of contact with soil and plants. Those are the conditions in which fungi might thrive. And transport that to animals, you can easily see that that can be the case for animals that, for example, gets in touch too much with, metal stuff or certain surfaces in the farm. And it is not necessarily dirty, but there's a lot of soil and there's a lot of other things. Those are things that can be a problem. I show at the end, I think, a couple of pictures, but it's not a big deal. So this is the vision of how the multiplication of fungi. In general, in order for you to have like this, especially the fungi, the other problem with fungi is that it goes all the way from spores. It can cause lots of problems. Cryptococcus is one of those problems. It's very common, for example, transmitted by pigeons, for example. But the other thing is that it goes all the way from very hardcore pathogenic ones like Cryptococcus to mushrooms that we eat. So fungi is this weird thing. You can have sexual multiplication, you can have asexual multiplication, you can have spores in soil that can last forever. So this is kind of the weird part for fungi. So that's why I think this slide is good for you to have it in your material. I'm not going to ask anything on it, okay? And there's no such a, in my opinion, there's no such an advantage of knowing the anatomy of the fungi as we have for the virus and the bacteria. Because for the virus and bacteria, at least we have some sense of how they multiply, what is needed. Although in virus we don't have much of a treatment, it's still useful. For bacteria, super useful, it's understandable. Like at the end, we're gonna go back to the bacterial anatomy and say, yeah, that's how freaking penicillin works, this is how other drugs works, cephalosporin works, and all the other antibiotics. But in this case, no. There's really not too much for us to learn. Starts with systemic mycosis. Most of the diseases from fungi, we call it mycosis, okay? And systemic ones, they have to be like deep infection in organs especially. Most of the time, when I'm talking here deep infection, I'm not talking about respiratory, urinary. Yeah, respiratory and urinary tract are deep enough for me, but these would be the most common things aside from the skin, okay, for you to have the infection. By the time you have urinary tract, relatively common, actually very common in humans, especially in females, is super common. Respiratory, less common. By the time you have respiratory fungi infections is bad enough, okay? And especially in this case because of the possibility to spread to other systems due to the close proximity of the vascular system. But the subcutaneous and cutaneous mycosis, these are the ones that are the most common ones, okay? So these are basically by contact, okay? Either with other animals, but mostly with what we call fomites, with surfaces in general that are around. So those are the most common ways of transmission for some of these mycosis. So we call it so you call subcutaneous, cutaneous, superficial. Again, this is derma. There's an R here, dermatomycosis. So again, it's mostly on contact. We call it this. Also, the other things that the other thing that actually tends to be a point for the transmission of some of these diseases is the kind of is very common in tropical climates. But as I said before, athletes, food disease, your feet inside of a sock, inside of your shoes, the whole day, it's a tropical climate there. Okay? It's wet, it's hot, it is, and if you don't take good care of it, it is a site to, basically reproduce or to spread the fungi. Fungi will be, I think, and the way we have to think about the fungi is the following. Once we die, the very first thing, or once you leave food, to throw, the very first thing that comes and colonizes that thing, even along with the bacteria, is fungi. And then you ask, where did that come from? It's everywhere. Okay? Spores and all the other things, the same way as bacteria, they are everywhere. You're just waiting for the opportunity to come in. Okay? But fungi even more than bacteria. Okay? So the very big recyclers of nature tend to be these guys first. They are the ones that do the heavy duty in terms of recycling of material. So it's sometimes, and for the most part, it's not because they are bad agents. It's just because you either contacting them too much, or because your immune system is gone and eventually you will too. So this is just two pictures of. This happens in a horse, cat, and here in the dog and horse and a horse here again. This is the stuff that happens when you have dermatomycosis, and this is at a very, very advanced, and to be honest with you, for the most part, especially in the developed world, very uncommon to happen. Why? Because for you to reach that stage of a skin infection by fungi, you have to just almost, those animals were forgotten, okay, for a long time in very bad places, okay, but it's there, it's around, it can be infected. This case here would be exactly the case of cryptococcosis, okay, so somehow this animal either ingested or aspirated something either in the soil or the feces of pigeons or stuff, and aspirated, and that thing colonized sometimes the sinuses of this cat. So this cryptococcus is, and you see these spores here. These are the spores of the fungi here, and you can have sort of pretty bad infection there. And this one here, this is what we call like the guttural pouch in horses. So it's a certain space that goes here, pretty close to the ear of the horse, and it has it has a pretty good size, and it's not very common. But once you have this kind of infection, again, it is a place that is kind of a closed, sort of wet, warm. You can have, and you can see like in the upper respiratory tract, you can have lots of warm and wet places where that thing can go. The same way for the urinary tract. So those are really the places where you're going to have some degree of fungal diseases. The problem with this, in this case here for guttural pouch, is that this thing is very close to some of the nerves, the cranial nerves inside the horse's brain. So sometimes, the horse doesn't necessarily develop anything. It doesn't have bleeding or anything. But once that thing ruptures, then you can have like profuse bleeding. And sometimes even worse, you can have nerve damage because that thing is started to be too close to some of those cases. So as you saw on the fungi, it will be easier. If you have to, ketoconazole is one of the drugs that is pretty common to treat some of that. But they are mostly the ones that you see, for example, in humans. lots of them are over the counter, and lots of them is just topical. By the time you have to start treating these things, and which basically means, aside from those cases, these two cases here, you'd have to have some sort of systemic, treatment for those, and that becomes more of a problem because ketoconazole is not very good to your kidneys and liver, which is going to be the topic as we finish this class. That's going to be the topic of the next class. So let's wrap this thing up here and let's start the pharmacological principle class. There we go. So before we start, let's have a 5-minute break before I fuel myself and you. So nobody had any costumes? We had an avocado. We have an avocado. You You can. I said I had a super idea. Next year, I'm gonna come as a placenta. I know. I just had the idea in the class now in 312. And imagine cotyledons, placentums come out, and I am the fetus. Like, come on. And you go like without a face or anything, and people go like, what is that? Because the placenta is not exactly something, wow, it's a placenta. It's like, what was the other thing that I said that I would do too?
Oh, your daughter be an embryo?
Oh yeah, Giovanna, my daughter, could be an embryo too. We could be twins. And then the other, no, I had another one. What was that? Yes, something to squirt liquid, like the amniotic fluid, and people pass by and you're like, it is gross, but it would be nice. You have to, huh? It would be nice. It would be nice. Who would think of eating a placenta? This is super original. In a reproduction class. That's it. Next year. And you can be also super specific. You know what it can be too? Janet, I can be a cotyledonary placenta. Giovanna can be a zonary placenta. Belt a placenta for longer. Oh, glorious. It would be nice. It would be nice. Oh my God.
question for you guys. So next week's class for the week after, we have like labs, but for Tuesday, would you guys rather have case studies or time to work on your presentations? Because the first round of presentations is the 14th, and then the following weeks will be presentations each day. So if you want case studies, we can do case studies. But if you'd rather work on your presentation, we can do that instead. I'll leave it up to you guys if you want to like report back maybe Tuesday with your decision or. Okay, perfect. You're all leaning towards that. You look very unsure.
I was reading that.
On November 12th, that's like a week and a half from now, we don't have class. Case studies or time to work on presentations? Trying to figure out what people prefer. Yeah, because on the 14th, it's the first round of presentations for, I think, 2 groups. No, on the 14th, so change your decision.
And that's when we have the quiz too, right?
The quiz will be on the 12th. Yeah.
The quiz is not next week?
No. I sent out an email saying it's on the 12th. Did you guys receive the email? Okay. Okay, perfect. I'm always so concerned when sending sending messages through Canvas because it never says if they're delivered or not.
Okay, next and last quiz will be on November 12th.
Okay.
So after the quiz, are we going to do case studies?
Yes. That's the question?
After the quiz, case studies or to work on presentations?
You're the ones who are presenting on the 14th, so consider your answer.
I'm fine with that.
Case studies.
All right.
Jen, for like the last big quiz, is it on like the very last day of class?
Yeah.
What days?
That's the 28th.
Okay. Sorry. I got caught up with the placenta idea. Apparently, people approve.
I regret Googling.
Oh, you saw it?
I saw one of this woman who's just had a t-shirt that looked like a placenta, but then there's an attachment to a man who's dressed as a baby.
Oh, that is gross. I'm gonna be attached to my daughter. Hey, you're alive still. Like that. Okay.
Oh my God.
I know, it's super gross. So let's go to the very final class, our slide class or slide for this class, which will be I'll try to finalize this, and then in the next week we start presentations on.
Not next week.
Not next week. So what we can do is I think I won't be able to finalize this. We're gonna finalize this probably on Tuesday. Then on Thursday we still might have time to for a case study, especially for the last 2 classes combination. And then the case studies will start to really, I believe, look more like the presentations and more discussions and so on. So for the pharmacology, I think before we even go to the antibiotics, and I focus on antibiotics and anti-inflammatory, basically because they are the 2 biggest weapons that people have. Obviously, you can go all the way from antiviral, diuretics, or you name it. There is a ton of classes of drugs that we can study. But let's leave whatever that is aside from antibiotics and inflammatory to the specific cases. Okay, so again, the class is not designed for us to learn everything about pathology, everything about pharmacology. It's just to give you some ideas that you guys can work on. So on the pharmacology, these two words, pharmacokinetics and pharmacodynamics, are actually as important, for us to have somewhat of an idea than actually knowing what class of antibiotics we're going to study and so on. Why? First of all, because by the time we start into the therapeutics, and that will apply to every drug, actually applies to everything you put inside your body. This thing, everything that you put inside of your body will have some sort of route inside of you, all the way from absorption to distribution, and then to somehow metabolization for metabolites from those molecules eventually after use, and then you have the excretion. Why would that be, or obviously that's super important? Because first of all, you want to know if it is a molecule like any other, like glucose. There is a way in which that glucose will have to be absorbed. It goes to your liver. Sometimes it can be oxidized. Sometimes it can be basically become glycogen, or it can be transported to other cells. It gets inside of the cell, but can only get inside the cell if you have insulin. And after that, it can be oxidized, or if you eat too much of that, it can become fat. Okay. Eventually, after that, it can go all the way around, being synthesized, and eventually you're going to excrete something, water and CO2. Okay, so that's knowing somewhat of that route. It helps you, think about a little bit, on how that thing and how you do it. The pharmacodynamics, it has more to do with the tissue responses, physiological mechanisms, and how it works. So for antibiotics or anti-inflammatories, like the other day I was watching one of those documentaries about former NFL players. What happened, to a bunch of them is that aside from going broke, because they spend all the money, the second part is lots of them with serious muscle bone injuries, that they cannot walk well, they cannot, they have mechanical problems, for obvious reasons. But one of the things that is coming up more and more, one, I think you guys have heard about it, which is the concussion, problems they have. So they end up having or developing a sort or some form of encephalopathy, so they end up going crazy, basically speaking. But the other one is because of the nature of the sport, and they suffer pain for most of their career. And some of them, in certain positions, they have to take anti-inflammatory, heavy steroidal anti-inflammatory drugs. In order to even go say, I have to play tomorrow because otherwise I'm not going to get any money. And they take for months, years, and so on. So right now, you're starting to have a bunch of former NFL players with insufficient kidneys. So their kidneys basically shut down, don't work. Something happened there. And this is biotransformation and excretion. Okay? So they had relatively healthy kidneys, and a lot of times also livers, and eventually they had problems because they took too much of it. Another one, so in that case, there are the reason why some of these drugs take so long to go from research to actual clinical trials is because they have to test all of that. FDA takes forever to approve something just based on that. Okay, so they have to go and you have to do it in animals, and then you euthanize animals, you collect every possible tissue in that animal and see if there are, for example, what happened to the tissue? Are there residues of this drug in this tissue? Are, what is the long-term effect, or is the short-term effect, or is the medium-term effect, and blah, 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 blah. So they try to do the best they can, to approve some of that. So absorption and distribution, and let's start with, for example, this very, very clinical thing, that is, how do you basically give a drug to an animal or to someone? And let's think, for example, on the very first thing that comes to your mind when you have to actually give a drug to treat a certain condition. Most of the drugs in humans that we take are what route? Oral. Why? What is the biological reason we give oral? That would be, but faster absorption? Oh, IV would be a lot faster. But it's because it's not a biological reason, it's because it's easier. It's basically it's more convenient. And in many cases, you're going to see, obviously we're not going to be discussing those things, but in human medicine, in veterinary medicine, you think a lot about that. Because one thing is for you to have the perfect drug against a certain condition. The other thing is for the owner or the person to take it. One of the major problems, for chronic diseases, I don't know if you have heard this, some startups that are starting to put little chips in the pill, very tiny. Why? Because they can make sure that the patient took the drug. And this is happening because at some point, especially for people in chronic conditions, they have to take so many drugs that if they miss some, their whole treatment actually don't work well. So the problem here, we're not going to go into the human side, but this is one of those things like this. Obviously, any of these routes, they have an advantage and a disadvantage. And they have certain things that you can give, depending on the molecule. You would probably always try to go into this, because it is not fecal but oral. You would try to do that.
With the variations in oral medication, with like tablets and capsules, like, is it the only reason why you choose a condition for like the speed of absorption, or is there another reason?
Yeah, but the speed of absorption, I think it will have more to do with the actual molecule than actually how they are. The capsule is basically a polyester or polyethylene thing that enclosures. The pill is basically the salt that they put it like they put very tight together, and that becomes like a certain shape. But if you put it into a little bit in your mouth and stuff, it would swallow. It doesn't necessarily, either one will not, both can be absorbed fast. The only thing is that it will depend more on the molecule itself than actually how enclosed they are. Unless you have a certain enclosure that say it is specifically designed to not break under very low pH, which might mean that a lot of that will only be released in the small intestine. You can have that. In ruminants, we have stuff that we try to do it to bypass the rumen, so it doesn't get into the bacterial fermentation and stuff, and only goes to the small intestine or the true stomach. So you can have all sorts of ways in order to do that. But oral would be the very first one because it is easier. Okay? Easier, I mean, especially for humans. For animals, it depends. If it is your dog or cat, can be, what if you have to give something to a herd? Or you have to give to groups of animals that are just far away. there's all sorts of, wild animals, they have all sorts of things, to how you choose to. Intravenous absorption, it's basically, it's not, you absorb. That's it. So you give it straight to the circulation. Intramuscle. Intramuscle, the thing is, it is not as fast absorbed as IV, and it depends on where you give that administration, that injection, because certain parts, certain muscles are more vascularized than others. There are certain things that you would like to give it in the muscle instead of any other route because you'd like to see vaccines, especially live vaccines. You'd like to give it in the muscle because they need to replicate a little. That vaccine, whatever you're giving to them, viruses, for example, you'd like them to, you would expect them to replicate a little. Subcutaneous and intraperitoneal. Intraperitoneal is not very common, but is in the peritoneum, which is somewhere in your belly. Especially subcutaneous, it tends to be slower release. Certain drugs you don't want to give too fast. And at the same time, you can give large quantities. So we mentioned at some point when you give, for example, you have a dehydrated animal, and you can give this physiological solution IV. You can make the animal drink water. The drink water it cannot take so much, especially if the animal is sick. When you're sick, you don't want to get off. You don't want to get off of your bed. You're like so tired and da da da. The other one is IV, so you can give relatively fast and straight. So if you want to recover a person, a little bit faster, you go IV. But if you want to give large amounts, subcutaneous would be one of the best ways to do it. You almost form like this little stacks, Why? Because it can go there, it will be absorbed slowly, and you can give in very large quantity. Spinal subdural, this is basically almost only used for anesthesia. Okay, the same way is going to be for dermal topical, that's self-explanatory, so it's just for surface stuff. But in inhalation, spinal and subdural, that's almost, I shouldn't say almost all, but 95% exclusive for anesthetics. So one is for one single type of anesthesia that you call epidural or subdural. And the idea is that you can block portions of your spinal cord. So that is almost always done at when you're trying to have somewhat of a local anesthesia at the very end of your spinal cord. Why? Because your spinal cord at the very end has a space without medulla, without the actual medulla. And they have direct contact with the medulla. So you can actually put a needle there without actually puncturing the medulla. Imagine if you're trying to do that and there is a medulla there. No, I want to keep walking. No, I know you want to give an anesthesia, but that's not much. But there is a point there at the very end. So women in labor, that's probably one of the most common reasons why women can take the epidural, is that you can give the anesthesia and all of a sudden everything from waist down is anesthetized. Okay? So you can have some comfort without the dangers of general anesthesia. Dangers of general anesthesia, and that's one of the reasons why you have inhalation anesthetics. Anesthetics, you can give something IV, and all of a sudden you're down. You cannot feel or do anything. The problem with general anesthetics is that general anesthetics are In anesthesia, you deal with your cardiovascular, your kidneys, your lungs, your liver all the time because you have to metabolize a lot of drugs. And the problem with general anesthesia is that if you, and this is a word that is used a lot, if you induce anesthesia, when you say inducing is like starting the anesthesia, and that thing goes too deep, you have to bring the system back. And when I say too deep, normally you're talking about cardiovascular. Okay, you basically stop your heart. And the advantage of inhalation or anesthesia that you actually breathe is that you can control the amount. Once you give the anesthetics in IV, that's it. You gave it too much. Oops, that's it. When you're inhaling, you're basically getting a little bit of that anesthetic every time you breathe. So you are there, you're breathing, you are under anesthesia. You go a little further, you just decrease the amount of anesthetic. In the next breath, you're going to have less anesthetics going. So you control more. So you see, this is one of those examples where the route matters. Now, for our cases, how much of that talk about anesthetics will matter? Very few cases, you're going to have something like that. But the reason why you choose some of that are not always biological. I think that's where I want to go back to. Sometimes you give it because it is convenient. Now, how do you choose some of those things? It has to do, especially to do with the portion, not the process absorption, but it has to do with excretion and also the metabolization. Let's say, for example, absorption too. Why there are certain drugs that you simply cannot give orally? There are certain drugs or certain proteins that if you give it orally, it's going to be denatured by the stomach. Okay? This is one common thing that happens. The other thing is, depends on the absorption. Let's say you have molecules that are, and then you go back to the basic structure of some of these molecules. Some of these molecules are too negatively charged. Some of these molecules are too positively charged. Or some of these molecules basically have dissociation constants, pKa or something. They are too different than either your intestines or even your stomach. Sometimes you want your stomach to absorb certain things. But the thing is, this has to do with the biochemical and biophysical properties of each molecule, and especially on the absorption side. By the time it comes to excretion, renal will be by far the most. You're going to see the most metabolization, the most will occur in the liver, excretion, the most will occur in the kidneys. However, you're going to see a lot of drugs being excreted by multiple routes. It's going to be mostly kidneys, but you're going to have a little bit in the feces too. And when you say in the feces, you can tie the feces with the liver. Why? Because most of these drugs will be metabolized in the liver. Sometimes the liver takes some of those and throw them to the bladder, to the bile salts. And then it goes from the bile salts to the feces and then gets excreted. Okay? Some of these things, the way they are excreted, as I said before, the same way they are absorbed, it matters their biochemical, biophysical properties. The same way happens to the excretion. Okay? Sometimes the urine pH matters. Sometimes drugs that work well in humans do not work well in ruminants, or non-ruminants work well in ruminants. Why? Because the pH, for example, of urine in non-ruminants is very different than the pH of ruminants, especially carnivores. Carnivores, their pH is very different. Why? Because the way, or especially because of their diet, normally pH, our urine pH tends to be more on the acidic side, 5 to 7. pHs of normally herbivores in general tends to be more basic, more to the 7, 8, 9, even 7, 8 in general. So that can have some effect on how you excrete. Why? Because sometimes, depending on if your dissociation constant for that drug, because all the drugs will come in the form of salt. So you have some antibiotics, and you always have like it's something. I think you see in many of it's something, and then HCl, or something and sulfate something, or hydrochloric something, or why? Because it has to come with a salt. And depending on how that thing dissociates is where you're going to have some problems and how it is going to be used first and how it can be dissociated and how it can actually flow out after you have done the action, in a certain site. When it comes to when it goes back to the kidneys, it has to be in a certain pH in order to actually be filtered and then get out of the system, okay? Biliary, I said the same, is somewhere the same, but then happening in the liver and then conjugated, into the bile and then going to the feces. Milk, saliva, expired air, tears and sweat, all of them can have, or you will have some excretion through those routes, but they tend to be mostly residue. So when we talk about, you give it a certain drug to an animal, and all of a sudden you have like milk, which is the one that I'm close to. If you give some or most types of antibiotics, if you give it to an animal, you have to withhold the milk for a certain number of days. And when you say withhold, you have to dump that milk. You cannot let that milk go into the tank. Oh, is it a lot of antibiotics? No, it's residue. Well, the regulations say if you have that amount of residue, that milk is gone. Okay? So which basically means, yes, you do have some of that going to the milk, you do have some of that going to the saliva too, but they are not major routes. Okay? You're not going to have excretion of those, through those routes. Expired air, again, anesthetics, that's the major thing. And tears and sweat, to be honest, to begin with, they don't have even enough volume, to actually excrete a lot of that. Milk, you do have saliva in some species, such as the ruminants. You produce like a boatload of saliva every day. Obviously, milk, you produce a lot, so you would have the volume even to excrete stuff. Expired air is very specific, and tears and sweat, not even close. Okay? Very good. So let's start this. I'm not going to have much time, so let's just start with the antimicrobial, drug. So now that we have this sense of, what route and how we administer, some of these drugs and some of this excretion and so on, you're going to see probably in some of your case studies that if an animal is, or in the cases, we're not looking at case studies where you have to guess something. The cases given to you is like you go there, you see a case, you build more or less how you want to present, and some of those things you'll probably, as you read about that specific case, you're going to hear a lot about some of these points. So eventually they say, if you, for example, if you have, in one of the cases, you have something that deals with their, or is very toxic to their kidney, or you have a kidney that is damaged already, and you have a drug that is, it depends a lot on the kidneys being excreted, that's a problem. Or if you have a drug that is even more toxic to the kidney, and even, you can maybe kill the agent, but also kill your kidney in the process. So it's also doesn't necessarily go in the direction of curing the animal. So some of those little things will have nothing to do with the action of the drug into the agent, in treating the agent, the bacterial agent, the viruses, whatever. It has to do with how I shouldn't say toxic, but in how hard your body will have to work to sometimes get rid of that drug. Okay? And some drugs are only used, if you have a certain class of drugs, antibiotics, for example, that is, and I remember when I was in school, it is only used as the last resort. Why? Because if the other ones didn't work, and then you're like, okay, this animal will die. So let's try this class of antibiotics. And then people say, yeah, but the animal will suffer eventually. Either because of the liver or the kidneys, but it's the only thing left. Since it's not used all that much, sometimes you don't have much microbial resistance to that drug, but that's the extreme. I think it was even, who was taking antibiotics in my house? It was my wife. And she was taking, what was I forgot the class of antibiotics, but she started going like, oh, I'm like having tremors, I'm having this and that, and all of a sudden she's going there like, oh, and the worst thing you can happen is going to Google or YouTube. You start looking, oh, that's exactly what I have, and you're like, all of a sudden you have some sort of degenerative disease that you think you have, but at the end it's like that drug could cause or could have side effects that was probably as bad as what she was treating. So all of a sudden she stopped taking and she got better. So it is that side of treatments of antibiotics. You're going to see antibiotics. If you look at how antibiotics were discovered, is first by accident. Okay, penicillin. So penicillin, it is produced naturally in nature by what? What is the story of the accident that, gave rise to antibiotics? And which was basically this one. Penicillin was the first one. Okay. It is basically produced by some or a certain species of fungi. Okay. So this stuff is like, all of a sudden, and you're going to see, eventually you see that lots of species, they have some sort of antibiotic like molecules, because they don't want certain plants don't want other plants to grow around them, because it kind of it makes like a competition for nutrients, or bacteria against viruses, against fungi. It's a war out there. So they have molecules. So in this case, this guy found and isolated this molecule. And what is the revolution, and what is the stuff that came from the antibiotic, the study of antibiotics, that before it was so much more complicated for you to treat any bacterial infection. Think about today, when we were talking about the virus and bacteria stuff, and we said lots of this stuff that we know today are still like kind of ancient. It's like lots of the physiology we know for a while. Antibiotics is one of those things that why people are so concerned today with antibiotic resistance. Now people are being a little bit more, perhaps today, patient before giving antibiotics to people or even to animals. Is because it was the very first thing that you could inject in you, and you wouldn't have or have very little collateral effect in you, and basically kill the agent that was causing the disease. That was very, very uncommon. Anything else that even today, can you kill certain things by injecting? Yeah, chemotherapy. Yeah, it kills the cancer cells and you. Okay? So this stuff is, what came out of that is that this is a biological thing. It is a biological thing. You can inject it in you and have very, or not very little, but have a very tolerable degree of toxicity to you, to your kidneys, to your liver, and it still act on all the bacteria or whatever that is inside of you. So all of this, all the way from cell wall synthesis, folic acid metabolism, protein synthesis that is specific for bacteria, DNA and RNA replication, which encompasses almost all of those. Different antibiotics will act in different mechanisms inside of the bacteria. And that's why you can have certain types, especially like some of these are, especially these ones here too, they tend to be more like what we call broad spectrum, because they tend to act on something that is very core to the life of any bacteria, DNA and RNA replication. You're going to have that. Some of other ones are going to be more specific to certain types of bacteria. Okay? Some of them depend more on folic acid. Some of them, obviously, you know, they have big cell walls, like gram-positive bacteria. So penicillin tend to be in the beginning only. Now you have different kinds, synthetics, different generations of antibiotics that can act more broad spectrum. But you're going to see that certain bacteria, maybe, or certain diseases, you have almost like one or two types of antibiotics that you normally associate with that disease to be treated. One, because of the type of action it has on the bacteria, but don't forget about that portion of absorption and distribution. Some drugs we use because they can just cross certain barriers that other drugs can't. Take, for example, certain conditions in the brain. You're going to need to have an antibiotic that crosses the blood-brain barrier, which is not very common to have. So you're going to have to find a specific one. Is it the best to treat the bacteria that infected your brain? No, but it's the only one that reaches the brain. Okay? So that's the kind of thought process that goes into choosing what type of this. Anti-inflammatories, as we go on, we need to go now, but anti-inflammatories will be a slightly different story. Why? Because then you're trying to basically cut the inflammation systemically. So that becomes a different thing. Unless you give it to very, in a very specific way. Let's say you give anti-inflammatories to treat your knees. So you give an infusion of anti-inflammatory inside the capsule of your knee. Then is a different story. But aside from that, anti-inflammatories have less of a, less of a concern about all these other things that we're talking about, administration, route, distribution, and where you act. Okay? Very good. So I see you guys.